So in algebraic models, as you recall from the very first classes, right, there's different classifications of models in RANDs, at least. There's maybe a few categories. One is algebraic, meaning it's probably a few algebraic equations or non-differential equation form. No extra equation. There's one equation, two, and multi-equations, which might be Reynolds stress type flows. So I think in the next few classes, this one's going to be kind of like more some of the stuff we've seen before Prandtl, but it's going to be merging into the models themselves. And I think next week we'll try and look at some models, and I'll also distribute their papers on Canvas. And I again apologize for not putting this one on Canvas yet. And I think the first ones we'll look at are probably Cebeci-Smith and Baldwin-Lomax, which is famous, and I'll distribute their journal articles. And maybe Johnson-King, and we'll also talk about the so-called half equation model, which is like a model between 0 equations and 1 equation. And we'll kind of try and look at some of those results and see how they are predictive for flows. So this is probably, I think, the last sort of more philosophical class before we get into looking at the actual models. And one of these models will be the one, the Baldwin-Lomax model, I think, will be the one that you implement in your 4th computer project. So we'll probably do that maybe Thursday, I assume next week. Or it could be that I have a conflict Thursday. I'll have to look at my calendar, but I'll send a note out to the whole class. So as you know, the simplest of all these types of turbulence models are indeed algebraic, and we need to create equations to close them. And as we saw before, this depends on the Boussinesq, eddy viscosity hypothesis. And somehow this needs to be used to close and compute the Reynolds stress. And it might also be that we need some length scales to close the model. And maybe a velocity scale, or like partial u, partial y or something. And you saw that earlier in Prandtl's work. And really, these models were created and argued for by molecular transport analogy. And one thing to remember is that for these reasons, they're called incomplete models. So an incomplete model is where, in the simplest terms, we need to specify something about the flow that's kind of part of the solution. And one example would be saying that the length scale is proportional to, say, the distance from the wall in a boundary layer. Right, so we've already said there's some statistics of the turbulence that's, before you even start our flow solver. So that's why it's incomplete. A complete turbulence model would be one where we say we don't specify something in advance about the solution. So a lot of these models, in fact, all the algebraic models that I've seen, maybe there's one that is complete, but I don't know it, but all the ones I've seen are all incomplete. And that's not necessarily a bad thing, because you'll see most of the one equation models are incomplete, and sometimes even models which uses more than 2 are incomplete. But there's a few classifications of complete turbulence models which are 2 equation ones. So usually you need at least a 2 equation model to have enough differential equations to close it without, like, close the systems of equation without specifying something about the solution in advance. A few other just general notes about algebraic models is obviously they're very useful for engineering as a design tool, even though, as I'll kind of mention if we get through this whole 7-page set of notes today, is that they kind of don't completely represent the physics as we know it, because they're based on this molecular analogy, and the molecular analogy is not consistent with what we observe in turbulent flows. And a lot of things have been designed with algebraic models because they're practical for calculating, things like skin friction really quickly. Another major advantage of the algebraic models, if you're okay with them not being totally physical and representative of turbulent flows, is that they're really, really, really simple to implement, really simple. And if you have a laminar flow code, just general Navier-Stokes, all you really have to do is assume some sort of length scale and have a closure equation for eddy viscosity and then model edit the viscosity in the code. And that's exactly what you'll do with just really only maybe 3 lines of code if you've done your laminar flow solver correctly to implement an algebraic model. And as you see, these are all conceptually very simple and rarely have numerical difficulties. What I mean by that is they're stable, and you don't usually have your solutions blowing up or returning not in numbers or having underflow or any of these other issues. They have good convergence, and they're cheap computationally. So those are all wonderful things, and they're really easy to use, as I mentioned, which will be in computer project number 4. Philosophically, as I just mentioned, they're incomplete. And that also implies, because they're just an algebraic closure, that they have to be finely tuned to flows. And it's difficult to extrapolate outside their calibration. So you'll notice that the minimum number of coefficients usually in these algebraic models is 3, and they're unknown, and you have to calibrate them. So maybe you have a solution and you pick these values to match a solution, like an experiment or a high-resolution CFD, and then you might apply this same set of coefficients, you keep them constant, and apply them to a more difficult flow, and the model wouldn't be predictive. So they're not great at extrapolating. In fact, there's one little tidbit, like say you're looking at a free shear flow, and you might look at just 4 different values. If you maybe just look at 4 different shear velocities, that's the difference, say, of U1 minus U2, like in a shear. Right, so that's a typical shear layer, U1, U2. You might actually have to have 4 different sets of coefficients. So it's not very general at all, because you're just looking at one flow, and you might have to have multiple sets of coefficients to get results which matches the measurements. So that's really frustrating. They do work well, maybe for a little bit better for boundary layers. This is all well and good, and there's been a lot of these algebraic models, like we mentioned, like Prandtl's model, von Karman's model, and these were mostly on paper and simple, and then digital computers came along in the 60s and 70s, and probably one of the most famous models that was used in the aerospace industry, at least, was by Cebeci-Smith. And this is what I think our first model will look at. And the CS model is interesting, as you'll see in the next classes, is it sort of combines the momentum integral theory of boundary layers with algebraic modeling. So a lot of the CFD done in the United States use this CS model for a long time. But it's sort of limited, and in the original models, you actually needed to know something about the boundary layer. You're tracking boundary layer statistics like thickness and momentum as you calculate the boundary layer. And that's something you might even need to prescribe in advance to get a solution. But it's practical, and it did great results for compressible flows. Some of this was overcome and generalized into a more or less incomplete model, I suppose you would say, by Baldwin and Lomax. And that's the next paper we'll probably look at. And the Baldwin and Lomax model doesn't really track any of these boundary layer statistics. So it got away from that, so I'll just call it the Baldwin-Lomax, or BL, not boundary layer, but Baldwin-Lomax. It doesn't track boundary layer statistics, and that was a huge advantage, statistics. And but at the end of the day, they produce similar results for a lot of flows. And they really focused a lot on the subsonic compressible flows. After that, there was a model which we'll try and look at briefly, and it's by Johnson and King. And this Johnson and King model is also incomplete, I should note. And of course, it has all the same shortcomings as all the other algebraic models. But it had some extra physics kind of built in, which we'll look at. And some of the advantages are, unlike these Cebeci-Smith and Baldwin-Lomax models, it could handle separation of the boundary layers, which is really good. And it was really formulated for wall-bounded flows, so you can imagine if the flow separates from the boundary layer with adverse pressure gradient, you can handle that. And it can also handle transonics, which is extremely important in aerospace. If you want to go to supersonic, you could go through the difficult regime of transonics. It's a Mach number of about 1, right, for transonic flow, where m is u over c, velocity divided by the speed of sound. And it really kind of took over from the Baldwin-Lomax type models in CFD prediction for aircraft design. Okay, those are probably the 3 models I think we'll try and talk about, and we'll pay a special attention to Baldwin-Lomax. And you'll see in these papers, they're sometimes pretty concise, short papers. And I'll share those on Canvas. You can look at them in advance of our discussion. And I'll make some notes, and we'll look at predictions, and also just look through the original paper to see how they think. And trying to understand how these people created a model which obviously was integrated in tons of CFD codes. I want to briefly go back to the ideas of molecular transport of momentum in this molecular theory, which we talked about previously, and just hit a few major points, because I don't know if I completely covered it the first time. And so we already mentioned some of this, and but it goes back to the Boussinesq hypothesis, in that there was like an analogy between molecular motion and turbulence, right? And at first glance, you might say they're not very different. But we'll kind of look at this in terms of the shear layer problem. So here's a picture from a book that was mentioning some of this. This is the y-axis, so it's the cross-stream direction, and this is just shear layer, which I kind of drew up here with U2 and U1. Except this is one that has a continual shear, so that means like partial U, partial Y is something like what? Yeah, some kind of constant, so it's increasing and it's greater than 0. And this is the streamwise direction, and you could say, well, if I just think of a gas as a bunch of molecules flying around, that's the molecular analogy, and then there's some mean free paths L, mean free path. So people like Boussinesq and Prandtl were actually looking at the turbulence problem, not like we think of it today as a continuum problem, but more of like these clumps of little molecules that are flying along. And if they travel in the x direction by, say, a unit 1, that they would also travel and expand as a clump and maybe like diffuse in a direction y. And so that mixing length originally was thought as L mean free path. That'd be like the mean free path that these molecules expand as you go downstream in the shear layer. And these 2 points P, Q would be, for instance, 2 types of points in the shear layer where these molecules might be. Also, in this type of flow, it's nice to note that there's like particular shear stress, which is tau xy. And we could write this flow as, say, u of y with the vector I, the x component. So that's what we're really seeing in figure 4.1. So we'll try and consider the momentum flux in the y direction across the y equals 0 plane. I'll just move that down. Okay, so as I noted, these molecules migrate across y, and there's going to be some momentum deficit, much like the momentum deficit that we looked at the last class in the outer layer of the boundary layer. And this is what is viewed as giving the shear stress. So if you look at the momentum equation of the Navier-Stokes equations, that momentum transfer in the y direction should kind of be balanced by the shear stress in a steady, statistically stationary flow. And that's a continuum hypothesis. And you would draw an analogy with, at the molecular level, of this same type of flow. So once again, we'll do a decomposition of these equations. We'll say u equals the mean plus a fluctuating part, where now u double prime would be the random molecular motion. And we might consider that the instantaneous flux across y equals 0 is proportional to the velocity normal to the plane, which is v double prime. So we have v double prime, v double prime. So we'll call instantaneous velocity in the x direction momentum as dp sub xy, and that'll be across a differential surface ds normal to the y direction. So you can kind of see that up here. This is normal to the y direction. So this is y. Normal to the y direction is orthogonal to that. And now we're going to take this equation and we're going to ensemble average it, which is represented to the bar. Let's say ensemble average. And then we note that the stress acting on y equals 0 plane will be written as the stress. Sigma xy is dp dxy ds across that surface x, which is orthogonal to y is 0. And here's the common definition in the Navier-Stokes equations for that stress. And Tij is the viscous stress tensor. And so we can write this term as that viscous stress tensor xy is the Reynolds stress. And this is incompressible, so I think I might have written it u prime prime v prime prime bar there. So I don't think I need to put the bar over the density. It's a constant. So this is like the Reynolds stress tensor, but this is just argued kind of with hand waving and dimensional analysis that this Reynolds stress tensor would be a lot like this stress tensor derived from like molecular transport theory, which is how Boussinesq and Prandtl kind of argued these things. And there's a wonderful book called Introduction to Turbulence, and it might have come out earlier. I'm not sure if this date's right. And Tenicus and Lumley, I think, Lumley was at Cornell. I think Tenicus used to be at Penn State, mechanical or aerospace, and went up there too, and they wrote these books and did research together, but you'll see their names a lot. And it's a great little thin book on turbulence, but it's not meant for beginners in my opinion. But anyway, they noted and talked about this stuff, and they said, when I re-looked at the book before talking about this, is that a stress that is generated as a momentum flux can always be written in this form. And they argued that the only real difference is that at the macroscopic level, the turbulent fluctuations U prime and V prime appear in place of the random molecular fluctuations. So this is sort of an analogy between the Reynolds stress and the molecular stress. So let's, keeping this in mind and thinking this is really the basis of the eddy viscosity approximation, that somehow we would need to derive a viscosity for a turbulence model that's algebraic from these molecular terms. So if we look back at figure 4.1, just to remind you for a second, you have it on the printout on your notes too, we'll try and use these gas kinetic theory again and try and find Txy in terms of Uy and the viscosity mu. So we'll say and note that the average molecular velocities is something like V sub TH. And that'll be what we'll call the thermal velocity. Why? Because it's related to the velocity of the gas, which might increase with increasing temperature. And we see that just in general gas, it goes as about 4/3 times the speed of sound, 4/3 c. Which is interesting. And about half in this shear flow, half the molecules will move in the positive y direction, while the other half move downwards, of course. And about the average vertical component of velocity, therefore, is about VTH, velocity thermal, times cosine of phi, and phi is angle from the vertical direction in the flow. So if we integrate over a hemisphere, the average velocity TH bar will be as VTH over 2. So we're going to write this momentum flux now using these arguments where we have momentum flux goes as VTH over 2 on average. So what we're going to do is we're going to write delta P negative. So that is, I have that written down as momentum, momentum flux from below. So that's what the negative means. And we'll also write an equation for momentum flux above. It's there and there. And so what do we have? We have some velocities times mean free paths. So that's the length times velocities, and times rho times this velocity. This, if you check the units, we'll get a momentum flux. I'm not going to go through all that right now in the interest of time. And it'll be as 1/4 times the density times thermal velocity times a length scale, the mean free paths times partial u partial y. And u bar, right, so that is, or capital U, that's the mean velocity as defined in the shear layer, as you see. So we can write these for the momentum flux, like going down through the surface and up through the surface of the shear layer. It's a partial u partial y is a constant. Okay, so now we have these two fluxes, and these are actually constructed, which I should note, from a Taylor series expansion, and where we've truncated higher order terms. And these momentum fluxes, you'll see, are really written in terms of the thermal velocities and mean free paths of the particles. It's not of the actual, like a continuum hypothesis. So you can now take these equations and add them, and then you'll get the net shear stress, right, which is the sum. So if we take these two equations, add them, we should get this right-hand side for the shear stress. And if you look back in the Navier-Stokes equations, the shear stress should go as, right, mu partial u partial y in the right-hand side of the momentum equation. And here, mu is our viscosity. So we should be able to relate the viscosity in the Navier-Stokes equations to something about this gas kinematic theory. And if we solve for mu, after putting all this in here, you'll have 1/2 of rho times the thermal velocity times the length of the mean free path between the particles. And so that's a funny way to write the viscosity, but it's kind of based on these arguments of a shear layer, of what viscosity should be to relate it to the gas theory. So this is just, remember, only a rough estimate of the true statistical nature of the flow. And a few other things. There's some assumptions we made, which are important to remember. I guess I should have boxed this equation because it's important. So of course, first we truncated the Taylor series. So that could be bad sometimes. And it's also noted from Tennikus and Lumley from their analysis that for this to be valid, we have to have this inequality be true, which is the length of the mean free path times the absolute value of partial 2u partial y squared must be much less than partial u partial y, which might happen in some situations. Anyway, so let's now define a length scale L, and we'll do it. So this capital L is not the length scale between mean free path collisions. This is a length scale just based on, I guess, the absolute values of the derivatives of the mean velocity and the shear layer. So that's fine. So this, just so you know, this is not the same as that mean free path. Okay. Other things for this theory to be valid is a Knudsen number. So we'll come back to that, because we rather work in length scales for algebraic models than mean free paths. The Knudsen number, I think we also talked about earlier in the class, should be the length of the mean free path divided by a length scale of, say, the flow. And this should be much less than 1 for our models to be valid. And I mean, most engineering applications, except hypervelocity rarefied flows, this will be true. So we don't usually have to worry too much about Knudsen number. It's just a measurement of how rarefied your flow is. So you can imagine that if you have I don't know, a length scale of your vehicle, if you don't do it with a fluid or a shear layer or boundary layer, and it's in the same order as the mean free path, then it's a rarefied flow. So you always want to make sure your Knudsen number is small for flows. So this is, of course, satisfied. A few notes on about all these equations, quick, is we also need to assume that U double prime is following a Maxwellian gas or molecules. So this is a first major important thing. This is the second major important thing. A few other notes. If we are looking at the number of collisions, should be much higher. The frequency of collisions than the, say, just like the time scale of turbulence, or smallest time scale. So that assumption is usually always built in because the number of collisions happen per second is much higher than, say, 1 over, the frequency of the smallest time scale or Kolmogorov scale. So the average time of, or between collisions is about length of the mean free path divided by the thermal velocity. And then a characteristic time scale of a shear flow might be something like the inverse partial u partial y. So if we want to form a length scale for the mean free path that relates the mean flow of the turbulence with, say, the velocity, the thermal velocity, just dimensional analysis might be the thermal velocity all over du dy magnitude. So that's one way to get, of course, length meters, units meters. So some things to note. This thermal velocity is the same order of magnitude as the speed of sound, order of magnitude, which we noted earlier. So V thermal is on the order of C bar. And I think earlier we said it was about 4/3, if I remember. And also that the mean free path is many orders of magnitude smaller than, say, the length scale L. Okay, so that's really the end of our notes on the molecular theory. And now we just want to take these major points and reconstruct the most basic algebraic models. And so based on this Boussinesq hypothesis and sort of hand-waving and order of magnitude analysis, this is where Prandtl came in and did his mixing length hypothesis. And I think it's interesting and that he didn't see it as a continuum, even though they had the Navier-Stokes equations. He visualized it as like clumps of these particles. So these clumps of these particles move downstream and they go down some distance y. That's y and this is x. And then this is proportional to some length scale. That's the mixing length. So when you think of people like Ludwig-Prandtl and von Karman, his student, they were thinking of mixing length as that spread of these clumps of particles. And sometimes students ask me a great question like, what is a turbulent eddy? If you ask Professor Prandtl that question, he would say it's nothing but a clump of particles that are coherent and move together in a turbulent flow. And a turbulent flow would consist of many clumps of these particles, all with their own little length scale. And a bad visualization of turbulence today might be like, oh, I take all these clumps of little particles going together and I add them all up, like a superposition, and that would give me like some sort of turbulent flow. And as I move away from the wall in a boundary layer, that I would have larger and larger clumps of particles moving downstream, and they would spread at larger rates as I go away from the wall. And that would be like his sort of way I think he looked at these turbulent models back then. So if we take this analogy of the molecular momentum transport for Prandtl's lumps of particles, and we replace L mix, we replace the length of the mean free path just with L mix, with our relations we used previously. And by analogy, he would write that the shear stress goes as 1/2 of the velocity of mixing times the length scale of mixing. So these are our typical velocity and length scales times partial u partial y. And to have a complete formulation, we got to close our equations. But we now have this term velocity mix, which we haven't specified. We might specify L mix as like the distance to the wall. So Prandtl, in his work, wrote an equation like 4.15. So you see here's velocity mix. That's the velocity scale. Goes as some constant times the length times partial, or du dy magnitude. And so this should give us units of meters per second. So you see, you have an idea of what L mix might be. Might go as something like the distance to the wall. That's the closure. But then he has, ooh, I got to get this velocity term. So he just related it to two other terms he knew. Because this way you have, I guess, one more equation to get rid of the unknown, right? So this is dimensionally correct. And whenever you write down an equation like this, just like we did here, it's always good to check the dimensions, as if it's not dimensionally correct, it shouldn't be wrong. And you also might note that truly L mix, the way he described it, is not a property of the fluid. For example, Andrei Kolmogorov would define, maybe use structure functions to try and find length scales. This is just sort of a philosophy definition. So that's a closure. Now, if you use these analogies, you can then relate it to the shear stress, and that'll go as like an eddy viscosity with partial u partial y. And this eddy viscosity could be closed with this model here, if you insert these equations, right? V mix and partial u partial y. Okay. If we want to go further and use Boussinesq's empirical eddy viscosity and Prandtl's mixing layer, if you combine all this, you'll see a few things. And if you make practical predictions, which you have a great difficulty using Prandtl's approach, because obviously he couldn't evaluate this easy for flows and compare them because he didn't have computers or excellent experimental apparatus. You might just say, well, for free shear layers, and jets, jets are my favorite flow, and wakes and mixing layers and a few other things, that length might be proportional to, say, the width of shear layer. Okay, and what do you notice about shear layers, jets, wakes, boundary layers? They're different turbulent flows, and they're going to have different widths. That is, the particles are, in his like lumped particle philosophy, they're going to be growing at different rates. And so they're all going to require different models for closure to be accurate, which is really, really bad. So in a sense, I need to know something about the physics in the solution before I even run my code, if I program this in a code. So it's not very general at all. And so this boils down to I need different proportionality coefficients. So I would need to like recalibrate my model for each case, and that's not very useful. So let's look back at this equation here, 4.17, which was came from this analysis, right? Molecular analogy. And you'll see that no matter how many ways you do this, this is just one way in the way kind of Prandtl thought about it and von Karman, you could actually kind of come up with these same parameters sort of with just different arguments. And but you always kind of arrive at the same thing, and that's because at the end of the day, you really only have two important dimensional scales to work with in these flows. One is L mix, and the other is partial U, partial Y for shear flows. Now, if you do this dimensional analysis, you'll always, or if you use Buckingham pi theory, identify pi factors, you'll find that this is basically the only way to come up with this using the molecular analogy. And this is a model which is probably most commonly used. You have negative Reynolds stress, goes as L mix squared times the absolute magnitude of the shear times the shear. So here, where did V mix go? Well, it's built into here like we showed up in an earlier equation, and it's proportional to the average of V prime. E.g., I have V RMS, let's see for the V prime squared bar and a half. And so if you kind of compare this to equation 4.18 to measurement, there's a paper by Townsend in 1976 where he writes this equation for an incompressible shear layer. So here's the magnitude of the Reynolds stress, goes as a constant times URMS times VRMS. And if you argue that VRMS goes as V mix, then these equation 415, 418. Let's go look at 415. Here V mix is a constant times L mix partial U partial Y. I guess you can deduce that these are the same order of magnitude. And that's what's argued in this Townsend paper. This is here. So this model of Prandtl and von Karman, according to measurement and analysis, shows that VRMS is proportional to URMS, right? But the measurements, and this is where we're in trouble, show in like a low-speed incompressible shear layer that URMS is about 25% to 75% larger than VRMS. And you can do that in the lab today. So the molecular analogy and leading to this simple closure for shear layers has a number of problems. And what are those problems? I think what we'll do is note them rigorously in the next lecture, but I can summarize them right now for you. Is that one, of course, they don't agree with measurement. So the statistics of turbulence, URMS versus VRMS, are going to be equal in terms of the prediction. So that's not good. And I think that's one of the main problems. And the second one is it's not very predictive for more complicated flows at all. And you would need to have a unique closure coefficient for not only different flows, but even the same flows, like just a class of shear layers. So if you just have shear layers at different velocities between them, you would need a different closure coefficient for each case. So you might as well know the solution in advance for every type of flow predicted by Prandtl's model in practice. But don't be too critical of Prandtl because he didn't have digital computers through his whole life. And it took about 50 to 70 years approximately for people to get good enough measurements to really invalidate his model with computers. Okay? So I think with that, we're going to stop here, and we'll come back and make some more detailed notes on the shortcomings of this Boussinesq approximation. But you'll see it remains the basis for a lot of models today. So thank you.